Okay, so using our power counting analysis, okay, our master formula here in the blue box, we've managed to understand why phi to the 4 theory and d is equal to 4 really is renormalizable. And it's because there's a finite number of Feynman diagrams that diverge, so they can be removed with a finite number of matching conditions. But now that we have this nice equation, let's analyze another example. Let's study r is equal to 6. So if we're studying r is equal to 6, now we would be studying a theory for which we have a gamma integral d dx phi to the power of 6, and gamma is just the coupling constant. Okay, let's still work in d is equal to 4 dimensions. Then what is d equal to? Well, again, it is 4 minus e, so that doesn't change, plus n. Now, r times by d, that's 6 times 4 is 24, divided by 2 is 12, minus 4 minus 6. So 12 minus 10 is 2, so we get 4 minus e plus 2n. Now notice, for any e, if n is big enough, then d will be positive, and that means we have a divergence. Okay, and remember, the only reason why I say that is because our integral I, or Feynman diagonal, behave like lambda to the power of d. So positive powers of d mean divergences. So this theory has an infinite number of divergent Feynman diagrams. So infinite number of divergent diagrams. Okay. And so let's see why. Okay, so remember that when we had phi to the 6 in phi 4, you know, the only new kinds of diagrams that we could draw was stuff like this, and that wasn't a new divergence. But for phi to the 6 in this theory, we can have stuff like this. And that really is divergent. It's divergent. And you can't blame this on some lower divergence. Like we said here before, remember, we said we could have stuff like this. So there's 1, 2, 3, 4, 5, 6 external legs. This was divergent, but come on, this is something that we saw already in the E is equal to 4 correlator. Well, this is new. So there really are an infinite number of new divergences. There's an infinite number of divergent diagrams, and we cannot remove those with a finite number of renormalization conditions. So R is equal to 6, D is equal to 4. This theory is not renormalizable. Okay. So phi 4 we found was renormalizable. This is a theory that's not renormalizable. And what's the difference? It's the fact that now we've got this 2n appearing. This is what the new effect is. Now, let's do one more example. So let's, for example, so let's just, this is our master formula. So let's get a copy of it. Let's say that we still study R is equal to 4. So let's say we will still study R is equal to 4. So that means we have something like a phi 4 theory, but let's put D is equal to 3, okay? And let's see what happens now. Well, in this case, what is D equal to? So D will be equal to 3. And then 1 minus 3 over 2 is minus E over 2. And then we've got plus n times pi. Now, r times by d is 3 times 4 is 12 divided by 2 is 6, minus d, which is minus 3, minus r, which is minus 4. So this is 3 minus e over 2 minus n. So notice this, this dependence. So let's maybe stress this. This is an important point. When we were studying the 5-4 theory, over here we had plus 0 times by n, okay? So this term didn't appear, and this theory was renormalizable. For this case over here, when r is equal to 6 and d is equal to 4, we had n appearing with a positive coefficient, okay? And this meant the more vertices we put into the diagram, the more divergent the diagram was. And we could see here, we got new divergences at every order in perturbation theory. In this new case, where r is 4 and d is equal to 3, now there's a minus n. And what this means is the more vertices, the better the diagram converges. Okay, so convergence is actually improved by adding vertices, and this is often called super renormalizable. Okay, so super renormalizable. You really only have a finite number of different Feynman diagrams that diverge. Not just looking at the correlators, there's actually only a finite number of diagrams that diverge. But I hope that what is becoming clear to you is that this coefficient that sits here, this is the important piece of this formula. If it's positive, the theory is not renormalizable. If it's 0, the theory is just renormalizable. And if it's negative, the theory is super renormalizable. Well, if that coefficient is playing such an important role, it has to have some sort of a physical interpretation. So let's try to see what possible physical interpretation that coefficient could have. Okay, and I don't think that we need to keep this, so let me get rid of this for now. Okay, you've got the point. So let's just get rid of that. Good. Okay, so to actually understand what that coefficient is, I'm going to ask you to consider the following. So let's study an action. It's going to have many terms in it. I'm just going to focus on a few of them, but it's the integral dd of x. We'll have a standard kinetic term for the scalar field. Okay, so that's a term that I'm going to worry about. Then we would have mass terms and all kinds of other coupling terms. We might also have a g r phi to the r term, and then all sorts of other terms. These are the two terms that I'm going to focus on. So the first thing is, notice that the action usually has dimensions of h bar, and we've set h bar equal to 1. So this is length to the power of 0. So in our choice of units, when h bar is equal to c is equal to 1, the action is actually dimensionless. Well, let's look at the first term in the action. So we've got integral dx, d mu phi. This is a term in the action, so this had better be L to the naught. And let's analyze these various contributions, okay? So the integral d dx, this is going to give us an L to the d. d mu will give us L to the minus 1. d mu will give us L to the minus 1. Phi will give us L to the d phi, and I don't know what d phi is. And this phi will give us L to the d phi. So let's try to figure out what d phi is. Well, clearly, d minus 1, so that's minus 2 plus 2, dimension of the field phi must be equal to 0. And that means that the dimension of the field phi is 2 minus d divided by 2. Okay, so that is what the field is. It's L to the 2 minus d over 2. Good. And let's just be completely explicit. D phi. Okay, very good. Now let's look at this term. We've got integral d dx g r y to the r. And this also must be L to the naught because this too is a term inside the action. Okay. And we know that we're going to say that GR, the dimensions of this is L to the, let's call it dGr. Okay. And let's see what this is. Okay. So looking at this expression over here. Okay, so sorry, let me move this out of the way. This is going to get in the way. Let's put that there. Or maybe put it there. And good. Here we have length to the d. Here we have length to the dgr. And here we have length to the r d phi. Okay? And this must be equal to length to the naught. So let's solve this equation. D of gr can be equal to minus d minus r d phi, which is minus d minus r times by 2 minus d over 2. And this is equal to minus d minus r from the first term plus rd over 2. So we learned that dgr, the dimensions of this coupling, is rd over 2 minus d minus r. Okay? And now, take a look. This number sitting here, rd over 2 minus d minus r, is exactly what we said was important over here. So in fact, what we are learning is the thing that determines whether the theory is renormalizable or not is the dimension of the coupling constant. So what we have just proved is if the coupling has positive length dimension, so I mean the coupling is a length or a length squared or something like that, then the theory is not renormalizable. Okay? So if this is like the phi to the 6, you can check that that coupling is a length. Okay? So G6 is actually a length. If the coupling is dimensionless, then the theory is renormalizable. And this is like phi to the 4. And the dimension of G4 was length to the naught. And finally, if the coupling has negative length dimension, so for example, the coupling is an inverse length or inverse length squared, then the theory is super renormalizable. Okay, good. Okay, so now let's just analyze two nice examples. Let's analyze electrodynamics. Okay, so you know all about electrodynamics. So the force is equal to mass times acceleration, okay, d2, dx2. So in our units, mass is a length to the -1. And this is an acceleration, which is a length over time squared, or equivalently, because time is now measured in length, that's also a length to the -1. So in our units, forces are length to the -2, okay? Now think about the Coulomb potential. F would be equal to Q1, Q2 over 4 pi epsilon naught r squared. Well, 1 over r squared is 1 over length squared. So from this, you immediately know that Q1 and Q2 are dimensionless. So what do you learn? Quantum electrodynamics, QED, is renormalizable by power counting, okay? And this is, in fact, the theory that Feynman, Schwing, and Tominaga used to formulate renormalization theory, and you see this theory is renormalizable. What about gravity, okay? And let's think about just Newton's law of gravity. Well, in that case, Newton told us, oh, let me just put a mod here, okay? Newton told us that the magnitude of the force is his universal coupling M times by M1 times by M2 over R squared. Now let's analyze things. Remember that mass is an inverse length. So this thing sitting over here is an inverse length times an inverse length over a length squared. So this is a length to the minus 4. This is a length to the minus 2. So this means G has to be a length squared. That means positive length dimension. And this means gravity is not renormalizable. Okay, so gravity is not a renormalizable theory. It cannot be renormalized. Finally, let me just suggest you do one other exercise, which I think is very interesting. Inside this formula, our master formula over here, just ask yourself, what happens if D is equal to 2? If D is equal to 2, D is equal to 2 dimensions. This is like the quantum field theory that is defined on the world sheet of a string. So in string theory, you'll study two-dimensional quantum field theory because you're always studying quantum field theory on the world sheet of the string. And we think that there should be something special about that quantum field theory. But what happens if D is equal to 2? What happens to your superficial degree of divergence? So I'll leave that as something for you to puzzle over and think about. Good.